In this episode, the world's tallest roller coaster.
Looking back down on this ride from above, this is definitely something special.
Engineering that packs a punch.
Oh my God! The sensation of a launch, this is something akin to jet fighter stuff we're talking about.
And the pioneering historic innovations.
This is one of the last remaining rides of its type in existence anywhere in the world.
These are U.S. Navy F-18s. You can feel the power. What an experience.
That made the impossible possible. Ocean County, New Jersey. A quiet and unassuming region on the east coast of the United States. But just inland, in the apparently peaceful countryside, sits an engineering colossus. This is Kingda Ka, the tallest roller coaster in the world. And the fastest in the USA.
I've worked on a lot of different rides, but I've never done a ride this big or this fast. This definitely topped them all.
With jet-like acceleration.
Arms down, head back, hold on.
And twice as high as the Statue of Liberty at 456 feet. This finely tuned construction is a perfect balance of science and engineering genius. Roller coaster engineer Michael Wrights is central to its construction.
You take it when loaded, a 22,000-pound train, and you launch it up to 128 miles an hour in 3.5 seconds. That in and of itself is an amazing feat. But then you're also putting it on this tower that's huge and supporting the track and the train. And then in the end, you're stopping it. You're taking all that energy back out. The engineering that goes into that is a pretty amazing feat.
Situated at Six Flags Amusement Park, this record-breaking roller coaster has another engineering trick up its sleeve. Built within the structure of the 456-foot Top Hat Tower is Zumanjaro Drop of Doom. The highest and fastest drop ride ever built.
I think a ride of this size and this complexity doesn't come around very often. It takes a lot of time, and it takes a lot of money, and it takes a lot of energy to create something this dramatic.
Opened in 2005, this 950-meter adrenaline-fueled ride has pushed roller coaster design to its limits. A 12,500 peak horsepower launch system fires trains from 0 to 128 miles per hour in just 3.5 seconds. After scaling the 456-foot tower, riders plunge into a three-quarter spiral, crest a second hill, completing the ride in just under a minute. And daring engineering has incorporated Zumanjaro, a 415-foot, 90 miles per hour, so-called Drop of Doom. With each rise and fall, twist and turn, the rider experiences a mixture of acceleration or gravitational forces, which form the foundation of the ride experience. But to design and build a ride of this nature means pushing engineering to match the limits of human endurance.
We're always looking for ways to top something that's been done before. We want to have the steepest drop, or the most inversions, or the tallest, or the fastest. But it's hard to innovate. I mean, physics are physics, and you know, you can only do so much to the human body.
So how do you push the boundaries and build the highest and one of the fastest rides in the world? This would not have been possible without the work of daring innovators of the past. It's said that 17th century Russia was the birthplace of the roller coaster. Giant ice slides were constructed to amuse the likes of Catherine the Great.
Woohoo!
But they relied on the weather.
We are not amused.
Oi, that's my line.
In 1828 in Pennsylvania, a gravity railway was built to bring coal down from the mountains.
Yee-haw!
It proved so much fun that tourists were soon paying to use it too.
Scream if you want to go faster.
But while it took half an hour to ride down the mountain, it took 4 hours for mules to pull the carriage back to the start.
Bored now.
Fortunately, one man realized the mountains didn't have to be real.
Are you ready?
Oh, let's do this.
Science communicator Kate Mulcahy is in the Danish capital Copenhagen. Experiencing the ups and downs of a truly game-changing design.
This is the Rutscherbana, one of the last remaining rides of its type in existence anywhere in the world. Back in 1914, it was the pinnacle of roller coaster design. Its creator would go on to become known as the father of the gravity thrill ride.
American inventor Lamarcus Thompson was inspired by the gravity rides of the Pennsylvania Coal Railway. Opening his own version at Coney Island, New York, it was an instant success. But to stay ahead of the game, Thompson needed a new concept. And in 1887, introduced the Scenic Railway, a purpose-built ride that incorporated artificial scenery.
We're behind the scenes. We're so lucky we're actually walking on the track. Now, this is one of Thompson's original designs and is a huge leap forward from the Coney Island ride.
Thompson's American ride had purely taken passengers in a straight line. But his unprecedented Copenhagen creation takes a 625-meter figure-of-8 route, allowing passengers to get on and off at the same point. And his newfangled construction had another surprise innovation.
There's an electric motor that operates a chain lift that raises the passengers to the top of the 26-meter high hill you can see here behind me.
Once at the top, the laws of physics take over. As the cars roll down, gravity creates acceleration and kinetic energy, until the next hill forms potential energy. This pattern then repeats as the free-flowing roller coaster motion takes hold.
The Rutscherbana can reach speeds of up to 36 miles an hour. Now, because this ride relies on gravity alone, there's a brake person behind me. So if we get too fast, the brake person manually slows us down. Without that, there's a chance that the carriages might lift off the track.
With his breakthrough engineering, Thompson's scenic railways were in high demand. And by the end of 1888, his white-knuckle rides totaled 44 worldwide.
Thompson laid the foundation for the modern roller coaster. He was a genius of his time. And without his work, this wouldn't nearly be as much fun.
Back in New Jersey, design engineers have taken the basic principle of Thompson's gravity railway and supersized it, creating a record-breaking ride. By accessing the platform near the ride's 456-meter summit, it's clear just how far roller coaster engineering has come.
I'm not sure if we started with the idea of building the tallest ride in the world or if we started with building the fastest ride in the world. But essentially, those two things have the ability to go hand in hand.
Constructed from 1,400 tons of tubular steel and over 40,000 metal bolts, this truss frame construction is a modern engineering masterpiece. But like Thompson's scenic railway, it relies on a mixture of momentum and gravity to turn potential energy into kinetic energy. A ride of this scale, however, means rewriting the roller coaster rules. And today, Michael has the park to himself to put the ride through its paces.
So the easiest way to put energy into a roller coaster is what we've traditionally done. That's to take a train up to the top of a hill. This flips that on its head, and we're gonna put all of the energy in down on the ground.
And the energy needed is immense.
When the train launches, it's unlike any other coaster. Being pushed into the launch position, that amount of energy, I mean, from 0 to 120 miles per hour in 3.5 seconds, it's so intense, you're stuck to the seat, you can't move. I mean, you probably have never felt anything like it. Oh my God!
Known as an accelerator coaster, the kinetic energy needed is generated on launch. Once underway, the success of the ride relies on its design.
Wow, we are up at the top already.
Speed, height, and length of track is precisely calculated to complete the circuit. But crucially for passengers, the speed is converted into a ride experience that can be tolerated.
This misconception that people have of height and speed relating to G-forces, it's really only related to the accelerations. And as long as we stay within the accelerations that have been established and what the body is capable of handling, then we can go taller, we can go faster. That ride is intense every time.
The human body can't feel speed, only changes in speed. Engineers can build controlled acceleration into the track itself. The radius and gradient of each curve is carefully calculated to keep G-forces within the realms of pleasure, not pain.
Coming up with new ways to give people controlled fear, it can be challenging. It can be somewhat difficult because we've pushed the limits of physics and we've pushed the limits of building, but somehow or another we seem to keep doing it.
Engineers in New Jersey have succeeded in building one of the most audacious rides on the planet. But to fire this roller coaster over a 456-foot tower, over 500 times a day, engineers need to look to the past.
The pilots inside the plane experienced 6G. That's double what astronauts underwent during a space shuttle launch.
To create more impossible engineering. 50 miles south of New York City, engineers have altered the New Jersey landscape. Building the world's tallest roller coaster. Ingeniously incorporating the world's highest drop ride. For engineer Michael Wrights, this record-breaking coaster is a true game changer.
It's the tallest ride in the world. Up until recently, it was the fastest ride in the world, and it is a thrill that is unlike any other.
In this 500-acre park, Kingda Ka stands head and shoulders above the rest. But what truly makes it a standout ride is its start. Engineers have done away with the traditional lift and instead set themselves a huge challenge, launching a 10-ton train up a vertical mountain of steel, known as the Top Hat.
This launch system needs to be fast. It has to get that train over the top of that tower, and that's 456 feet. This presents some interesting challenges because you have to release all of this energy in a very, very short period of time.
In just 3.5 seconds, Kingda Ka must reach 128 miles per hour. Traditional chains or cogs simply wouldn't cope with such explosive energy. So how do you propel this super-fast train? It's an engineering challenge that would have been impossible without another great invention from the past.
Wow.
Engineer Andrew Smith is at the Patuxent Naval Air Station in Maryland, discovering an inspired breakthrough that transformed military aviation and holds the key to launching Kingda Ka.
You can feel the power. What an experience. These are U.S. Navy F-18s, and their pilots are currently training for one of the toughest challenges a naval aviator will ever face, taking off and landing on an aircraft carrier.
Since their introduction during the First World War, the aircraft carrier has made a massive impact. Huge flight decks allowed aircraft to take off and land unaided, opening up the skies. By the Second World War, a growing demand for these nautical giants had created a problem.
Producing large, expensive aircraft carriers in the numbers required just would not be possible. Finding a way then to put flight decks on smaller ships was the solution. But with a shorter deck to launch from, engineers would need to find a way to get up to takeoff speed faster over a shorter distance.
To find a solution, engineers would draw on a 2,500-year-old Chinese invention.
This is a crossbow. What makes it such a game-changing piece of engineering is its ability to store energy and release it on demand. So I pull back the string, lock it, and then we're going to load the arrow. All the energy is stored in the string and in the bow, and when I pull the trigger, the energy will be released. Whoa, not bad.
Naval engineers look to harness this explosive release to downsize their aircraft carriers. With the advent of jets, British Commander Colin Mitchell suggested launching aircraft with a catapult powered by steam from a ship's boiler.
The secret of the steam catapult lies beneath the runway. Beneath me are 2 cylinders with 2 pistons connected to this shuttle, which connects to the aircraft.
This connection to the plane's nose gear involves 2 tow bars, one attached to a slot in the shuttle, the other at the back of the wheel, keeping the shuttle in place during takeoff.
At the point of launch, pressurized steam is released into the cylinders, forcing the aircraft down the runway.
The F-18 remains attached to its shuttle for the length of a football pitch before the tow bar disengages, releasing the plane. The energy produced is so extreme, the jets are propelled to take off in just a quarter of the normal runway required.
The pilots inside the plane experience 6G. That's double what astronauts underwent during a space shuttle launch. Mitchell's design went on to redefine the aircraft carrier, making it possible to launch heavier and heavier jets. To this day, his design is used by navies around the globe.
In New Jersey, engineer Michael Wrights and his team are taking the catapult launch concept to fire off one of the world's fastest roller coasters.
The sensation of a launch on this ride is unlike anything you've ever felt. Like a super bike, the acceleration might be half as much. I mean, this is something akin to jet fighter stuff we're talking about.
And like an F-18 jet, the hydraulic launch has its own catapult system to propel a 10-ton train. Its crucial component being a track-mounted shuttle called a catch car.
Right here is the start of the launch track. And This red piece in the middle is a catch car. This is what connects to the bottom of the train when it's launching. Being driven to the launch point right now. At the front of the catch car, there are 2 cables attached. Those 2 cables pull the catch car down the launch track. Crossing over the catch car now.
As the train rolls into its ready position, a lever known as a dog connects the train to the catch car.
So the dog is on the bottom of the train, and when the train comes into the launch position, it falls inside of this pocket. In just a second, we'll hear the dog drop from the bottom of the train. There it is.
With the launch catapult in place,
Rolled back, we're locked and loaded.
the roller coaster is now ready for one of the leisure world's most phenomenal engineering achievements.
Arms set. Head back. Hold on.
With the catch car disengaging at 600 meters, pure momentum propels Michael up a 90-degree vertical track.
Staring at the ground. Oh, man. It never gets old.
With acceleration that outstrips a Formula One car, the launch is an extraordinary feat, but the catapult would not have its punch without power. The solution to finding this energy lies with another of history's great innovations. Physicist Andrew Steele is in the English port of Grimsby, the birthplace of an energy storage system now exploited throughout the world.
When this tower was opened in 1854, it was actually the world's tallest non-religious building. And even today, it stands high above everything else here in Grimsby Docks.
But this tower's massive scale also stands for a huge engineering breakthrough.
It kick-started the ailing shipping industry here in Grimsby, and it's a milestone in one of the most fundamental technologies in engineering: hydraulics.
During the Industrial Revolution, Grimsby's desire to exploit trade with Europe was being stifled by an inaccessible, antiquated harbour. As regeneration took hold, engineer William Armstrong was called in. His biggest challenge, operating the harbour's huge new gates and cranes. His solution was water-powered hydraulics. But for this, he needed a high-pressure water supply. Realizing that height could provide the answer, he commissioned a 309-foot tower.
Check out this piece of engineering history. This is the guts of Armstrong's machine. The way it worked is that they would pump water from a nearby well up in this pipe, and it would go all the way to the top of this tower, about 100 meters above us, into a 150,000-litre tank. Now, for every meter that you give some water, the force of gravity means that you gain 0.1 atmospheres of pressure. So by the time you're all the way at the top of this thing, you're looking at about 10 atmospheres of hydraulic pressure.
Armstrong had created the world's first hydraulic accumulator. Due to gravity, water stored at height has accumulated pressure when released at ground level. From the tank, a vertical pipe connected to machinery on the dock below. Opening a valve on each machine released the now highly pressurized water, allowing gates to open and cranes to lift. Grimsby Tower turned around the harbour's fortunes, and although it now stands idle, Armstrong's hydraulic genius lives on. Over 150 years later, in New Jersey, engineers are harnessing hydraulics to rocket riders up the world's tallest roller coaster, Kingda Ka. With unique access, engineer Michael Wright is behind the scenes of this ingenious launch system.
Nobody really gets to see this amazing piece of machinery back here. This really is the heart of Kingda Ka. This is what enables us to launch that train.
Unlike Armstrong's gravity-fed 300-foot tower, Kingda Ka's hydraulic power is created by a myriad of cutting-edge technologies.
What you see in the middle is a giant reservoir holding a lot of the hydraulic fluid. Down below, there's 4 500 horsepower pumps. Those pumps pull the fluid out of that reservoir, and they pump it into this giant piston here.
As the piston fills, it's pushed in, compressing nitrogen that's stored in 4 accumulators. Once the system's charged, the valve on the piston is opened, and the pressurized nitrogen forces the fluid back out into the winch mechanism, launching the train above.
It happened so quickly, these accumulators are charged with the nitrogen to about 4,000 psi. For comparison, your car tire only takes about 40 psi. When we launch a train, no one's allowed to be inside this hydraulic room. It is a sight to see. It's like a thunderous roar in here.
The power of this technological marvel is truly impressive. But to complete America's fastest roller coaster, its designers must draw on more inspired inventions from the past.
Wow, for 100 years old, it still really packs a punch.
To produce more impossible engineering. In Jackson, New Jersey, engineers are pushing the boundaries of physics by creating one of the fastest and highest roller coasters on the planet. And combining it with the tallest and fastest drop ride ever built. Engineer Michael Wright was at the forefront of this audacious project.
They're fast, they're furious, they're probably one of the most intense rides you're ever going to get on.
Built over just 14 months using 1,400 tons of steel, the 456 feet tall mega ride Kingda Ka towers above everything in its vicinity and can be seen from as far as 20 miles away. A masterstroke in construction. This accelerator coaster is precisely engineered to exploit nature's gravitational forces whilst keeping the train on the tracks.
In a sense, what the rider feels, the train also feels. So that means that as you're at the bottom of the tower and you head into that curve, if it's sticking me in the seat, it's sticking the train to the track. When it twists, there's some lateral forces that would happen with the train, and guide wheels will help control that on the track.
On launch, the rider experiences linear G-force, being pushed back into the seat, and sudden climbs and turns, positive G-force, seemingly increasing weight. As the train is subjected to the same forces, making sure it remains firmly connected to the track is a design challenge. But perhaps the most problematic G-force to reckon with, but also the most fun, is zero or negative G.
One of the track elements that we like to include in rides is, people often refer to it as an airtime hill. And it could be a 0G hill, or it could be a negative G hill. That's all a result of the shape of the track, or the shape of the curve.
Negative G gives riders an exciting feeling of momentary weightlessness, which for the train poses a huge problem.
Again, what the rider feels, the train also feels. So the train wants to come off of the track. So that's what we have to design for in controlling the train with respect to those G-forces.
So how do you prevent a 22,000-pound fully loaded ride car from leaving the track in a state of negative G? Engineers would once again look to history's greatest innovators. Dr. Rhys Morgan has come to the seaside town of Blackpool, England, to experience an historic piece of roller coaster engineering.
This is the Pleasure Beach, the UK's first enclosed seaside amusement park. It's been here for over 100 years, and in that time it's provided adrenaline-fueled fun for millions of people.
Looking to emulate the success of New York's Coney Island amusement parks, in 1896, local entrepreneur William Bean started importing rides from around the world.
Those early rides were ingenious pieces of engineering, and some still remain today. But there's one ride in particular here that features a game-changing innovation. Hey, here we go. I have to say, it's about 10 years since I've been on a roller coaster. I'm really quite nervous. This is the Big Dipper, a wonderful piece of historic engineering genius. The wooden track is 1,000 meters long. The cars travel up to 35 miles per hour, and at its height, it's 20 meters. Here we go. Oh, 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 oh. Oh my gosh! It went faster and had bigger hills than any roller coaster previously. Oh. It's all because of one man and his genius design.
John Miller was an American designer and entrepreneur who patented over 100 key roller coaster innovations.
Wow, for 100 years old, it still really packs a punch.
Prior to Miller's design, engineers faced a problem. They could only design rides with relatively small hills, because as the trains accelerated down and then uphill, the high speed would cause them to lift off the track. To overcome the problem, an ingenious solution was found.
Oh wow, this is really exciting. So here we are underneath the roller coaster itself. And this is what it's all about. This is Miller's innovative design. These are the under friction or upstop wheels. They go underneath the track. Here's the track over here. You've got the running wheels on top. And then as the cars go up to the top of a hill, to prevent the cars from flying away, these upstop wheels just push against the bottom of the track. It's such a simple and elegant solution, and it absolutely revolutionized the way roller coasters were designed for the future.
The Big Dipper remains an icon of roller coaster engineering.
Wow, when you get to the top of the hill, you want to take off, but it's thanks to the upstop wheels that you're not flying into the air. Oh.
Upstop wheels allowed engineers to build bigger and faster, and they're still used on every roller coaster design today.
Oh my God! Get me off this thing!
Back in New Jersey, an ingenious combination of guide wheels, including Miller's upstop wheels, are crucial to the safety of the mega ride Kingda Ka.
This is one of the trains, and we're going to have a look at the wheels, which are controlling the motion of the train. And up top, what you'll see is, we call this a road wheel or a load wheel. Those are the wheels that the train runs on all the time. These are called the guide wheels. And they sit to the side of the track and they control the left-right motion of the train. These are called the upstop wheels.
Made of ultra-smooth and durable low-friction polyurethane, the upstop wheels make or break the coaster's success. To demonstrate their importance, Michael is once again taking to the coaster. After summiting the 456-foot tower, the train plunges vertically back down, generating enough kinetic energy to climb the ride's feature airtime, or zero-G hill, known as Camel's Back.
These upstop wheels are in contact with the track all the time, but they really don't come into play until the train feels a zero-G or a negative G, an area where the train wants to come off. When it wants to come off, these wheels engage hard and stop the train from lifting off the track.
As the 22,000-pound ride car crests the Camel's Back, both the rider and the train momentarily experience negative G.
Into the brakes! Wow.
The upstop wheels must stop the equivalent to the weight of 2 adult elephants from flying off the track.
There we are. Back home again. These upstop wheels are extremely important. That allows us to go faster, it allows us to go taller, it allows us to do the things we want to do, because without them, there's really no way this train is going to stay on the track.
The team in New Jersey are setting a new benchmark in extreme ride design. But to ensure each 128-mile-per-hour adrenaline-fueled journey comes safely to an end, engineers will have to look to the past.
It's putting lots of toll on the steering system, on the suspension, but above all the brakes.
To produce more impossible engineering. Engineers in New Jersey have changed the face of roller coaster design and created Kingda Ka, the fastest ride in North America. However, for Michael Wrights and the team, the record-breaking ride doesn't end there.
We are standing in the station of Zumanjaro, the tallest drop ride in the world. 415 feet tall, 90 miles an hour.
Ingeniously built within the roller coaster's top hat tower, the so-called drop of doom is driven by gravity alone. But with each 10 seconds, 90 miles per hour ride, for its designers, there's no doubting their #1 priority.
Anytime we design a ride, hands down, the most important thing to us is safety. And that means it has to stop. And it has to stop reliably, and it has to stop every single time.
Achieving this was a colossal engineering challenge.
You've got a fully loaded gondola. You're trying to stop thousands of pounds in a relatively short distance.
With the ride in constant use, a braking system susceptible to wear and tear is not an option. So how can Michael be sure the drop of doom will safely stop before it hits the ground? It's a problem that would need another genius solution from the past.
This is awesome! These souped-up pickup trucks are going at incredible speed!
Science communicator Kate Mulcahy is at Rockingham Racetrack in Northamptonshire, England, discovering the pitfalls of braking in the most demanding of environments.
When you've got vehicles travelling at such huge speeds, it's putting lots of toll on the steering system, on the suspension, but above all the brakes.
Vehicle braking systems have traditionally relied on friction, no matter how extreme the conditions. As Kate is finding out firsthand.
The way the brake system works is when the driver presses on the brake pedal, the brake pads press against the disc, and that friction slows us down. But that same friction also has adverse side effects. Awesome. That was awesome. What we're looking at here is the braking pad, which at the moment is in pretty good condition.
But if the pad is repeatedly subjected to high levels of friction, it's a different story.
Eventually this friction will wear down the brake pad, and if you let it get way too far, you can end up with this kind of erosion here, which can be actually quite dangerous.
Racing teams have the luxury of changing their pads after every outing. But if a vehicle has to rely on extreme braking for months on end, they need a different solution. Over 150 years ago, French physicist Léon Foucault made a discovery that would offer an ingenious alternative. He'd identified a peculiar phenomenon known as eddy currents, produced when a non-magnetic metal like copper was moved quickly through a magnetic field.
To demonstrate how eddy currents work, I'm going to do a very simple experiment using this apparatus here. First thing I have is a metal plate. It's made of copper. It's able to move freely on this slider, so it can slide up and down. And I have a little mount.
By introducing an egg, we can demonstrate the forces at work.
What I'm going to do is I'm going to release my plate, send it down and see what happens next. There it goes, it gathers speed. Ah! So now, this time I'm going to repeat the experiment, but I'm just going to introduce this very powerful magnet. So it's hovering over my metal plate.
As the copper is non-magnetic, when stationary, it's not attracted to the magnet.
So if I move my plate back up to the start, I'll add my second passenger.
But when it travels at speed, something magical happens.
We'll let it go, and hopefully we should see a difference. Wow, so there you have it. It slowed right down, and the question is why?
Despite the copper being non-magnetic, when in motion, the metal's electrically conductive qualities come into play, creating the eddy currents.
When my copper plate passed underneath the magnet, it was in a changing magnetic field. This induces circular currents, also known as eddy currents, and the magnetic force of those pushes against the magnetic force of the magnet, and that slows the plate down.
And when Foucault's amazing discovery is scaled up, it creates a brilliant braking solution, which can be used everywhere from high-speed trains to power tools. Back in New Jersey, Michael Wright is putting his faith in eddy current technology to bring the world's tallest drop ride to a stop.
Oh boy. We are just about at the top. What an amazing view. Oh my God, here we go. Oh, the anticipation. Oh boy! Oh! Woo-hoo! Whoa! Where are the brakes? Oh! Man, every time. That drop is so intense. Whew. It's a speed of about 90 miles per hour on that drop. That's a lot of energy. And to remove that energy, you have the braking, which starts about 150 feet off the ground.
Zumanjaro's track is fitted with a series of electrically conductive aluminium fins. As a gondola reaches them, magnets on its rear interact with the fins to create the crucial eddy currents to slow it down. It's a brilliant solution, as the effectiveness of the system only improves with speed, as demonstrated by Michael on solid ground.
What you have is two sets of magnets here, and in between the magnets, there's a gap. If I take this aluminum fin and I put it inside of this gap, I can feel a little bit of resistance. It's not too hard. But as soon as I try to put any kind of speed on that fin and move it quickly, it becomes nearly impossible to do. It's super hard. I can get a workout doing that.
So slowing down a 90-mile-per-hour gondola is no problem. And these innovative contactless brakes can do it time and time again, day in, day out, for months on end.
They are frictionless, they don't require much maintenance, and most importantly, they're on all the time. They're fail-safe. I would say that eddy current brakes kind of change the game in amusement rides because they're like a perfect solution. The beauty of magnetism.
With over 150 years of roller coaster development, for some, thrill ride design was reaching its limits. But with Zumanjaro and Kingda Ka, Michael Wrights and his team have pushed the boundaries once more.
This is definitely something special. Knowing that it was the tallest and the fastest and that I was part of that, it's cool. And seeing people come off it for the very first time, that just makes you happy.
By drawing from the pioneers of the past, adapting their ideas, and making discoveries of their own, engineers have taken roller coasters to a whole new level, making the impossible
Where are the brakes?
possible.
Looking back down on this ride from above, I remember when we built it, and that kind of takes you back to all the challenges and all the time spent making it a reality. You just get a little proud. You're proud of what you create.